Hello, in this video we will do an exercise on the Floor function. You're welcome in the channel of Mathematica. So in this video we will do this exercise on Floor function. We will present this exercise. Let x denote the image of x by the Floor function. Sometimes it's called also the integer part of x. We should prove that for any integer n, we have the sum from 0 to n minus 1 of the parts integer of x plus k over n is equal to nx. What do we have to know about the Floor function? For any real x, the integer part of x is an integer, which verifies the integer part of x is less or equal to x and is strictly less than, and x is strictly less than the part integer of x plus 1. Notice that the integer part of x verifies also the following properties. If n is an integer, then x plus n, or the integer part of x plus n, is equal to integer part of x plus n. The second property to know is that if x is not an integer, then the integer part of minus x is equal to minus the integer part of x minus 1. So let's start our problem, our resolving our exercise. For any k between 0 to n minus 1, we have k over n is between 0 and 1, which is natural because k is less than n. It follows that x plus k over n is between the integer part of x and the integer part of x plus 2. So we have two possibilities for the integer part of x plus k over n. Either it's equal to the integer part of x or the integer part of x plus 1, because the integer part of x and the integer part of x plus 1 are the only integers in the interval, this interval x and x plus 2. So we have this value of the integer part of x plus k over n, this part. So we should analyze when it will be equal to the integer of x and when it will be the integer part of x plus 1. So notice that x is the integer part of x plus x minus the integer part of x, where x minus the integer part of x is between 0 and 1. So we will replace the value of x in the integer part in the function on the Floor function. X plus k over n is equal to this expression. So here we have the integer part of x is an integer. So we can take it out and we get the integer part of x plus the integer part of x minus integer part of x plus k over n. Then we get two possibilities. Either this value is equal to 1 or is equal to 0. So if it's equal to 0, we get that the integer part of x plus k over n is equal to integer part of x. And this will be true when x minus the integer part of x plus k over n is less than 1. And we get the integer part of x plus 1 if this value is larger or greater than 1. So notice that x minus the integer part of x plus k over n is less than 1, equivalent to say that k is less than n times 1 by x plus the integer part of x. Let's denote lambda this expression. So we have, this means that the value of x plus k over n is equal to x if k is less than lambda and equal to x plus 1, integer part of x plus 1, if k is greater than lambda. Here we have a problem with the condition k is less than lambda. So we proved that lambda is the integer in which the situation change. So, but here we have some problem because since k is an integer, we might think that the condition k is less than lambda is equivalent to k is less or equal to the integer part of lambda. But this will be true if and only if lambda is not an integer, because else, namely, if lambda is an integer, we get k is strictly less than lambda. So that k will be less or equal to lambda minus 1, not lambda only. So we need to distinguish two cases, when lambda is not an integer and when lambda is an integer. So when lambda is not an integer, we get that the expression x plus k over n equal the integer part of x when k is less than the integer part of lambda, and the integer part of x plus k over n is equal to the integer part of x plus 1 if k is greater than the integer part of lambda plus 1. Then we have this sum will be split. We will split this sum from 0 to n minus 1 to the 0 to lambda. We get only the integer part of x. And from lambda plus 1 to n minus 1, we will get the integer part of x plus 1. So when we will compute this expression, we get lambda plus 1 times the integer part of x. And this expression is n minus 1 minus lambda minus 1 plus 1 times the integer part of x plus 1. When we compute this, after developing it, we get n times the integer part of x plus n minus the integer part of lambda minus 1. But here we have all these expressions are integers. So we can take it in the integer parts, in the Floor function. So we get the integer part of n times integer part of x plus n minus lambda minus 1. So recall now that the lambda is equal this expression. So we get that the sum is equal to integer part of n times x. Now we will show the other case when lambda is an integer. Here we get the integer part of x plus k over n is equal to integer part of x if k is less or equal lambda minus 1. Recall that lambda is an integer in this case. And the integer parts of x plus k over n is equal to the integer part of x plus 1 if k is greater or equal to lambda. So the sum will split like this. From 0 to lambda minus 1, we get the integer part of x. From lambda to n minus 1, we will get the integer part of x plus 1. So we have lambda minus 1 plus 1 times the integer part of x, also n minus 1 minus lambda plus 1 times the the integer part of x plus 1. When we compute this, we get the n times integer part of x plus n minus lambda. So they are all integers, so we can write it and in the Floer fraction. So recall that lambda is equal to this expression. We will replace it and we get exactly this condition. So we have finished and we have solved our exercise. So thank you for watching this video. I will meet you in the next video.